Okay, so we are going to start now on chapter 3, and this is a chapter really on Lorentz invariance. I think that a lot of this material is probably things that you know, so we're going to be reviewing things you know, but we'll do that to make the material more natural. So instead of starting with Lorentz invariance, let's start off and think about classical mechanics. So this, I think, is something that you will be very familiar with. One of the things that we talk about in classical mechanics is vectors, or 3 vectors. And I want to start off just by motivating why we want to talk in terms of 3 vectors. So 3 vectors, the classic example of a 3 vector is the position of a particle. This is usually what we want to work out. So x of t, this is a 3 vector. It's a collection of 3 numbers, x of t, y of t, and z of t. And this position, x of t, this position vector, will tell me where my particle is at any time t. Notice that on the left-hand side, I've got x with an arrow on top. That's the vector position of the particle. On the right-hand side, I've got 3 numbers, x of t, y of t, z of t, and these could be the coordinates of the particle in any particular coordinate system. X with a vector on top, x with an arrow on top is completely different to x without an arrow on top. So pay attention to that notation. When we want to write down Newton's second law, what does Newton's second law say? Well, it says F is equal to the mass times the acceleration, and the acceleration is the second derivative of x, vector x, with respect to t. Now, when we perform a transformation, for example, let's say we perform a rotation, no doubt the position vector x of t will change. So if I do a rotation, x of t, y of t, and z of t will mix up with each other. But it turns out that every single vector will transform in exactly the same way. So let's imagine, for concreteness, let's imagine that I perform a rotation. So x of t goes into x prime. Okay, this is a rotation. And I can write this out in terms of components. So x might be equal to x cosine theta plus y sine theta. I'm writing down an example of a rotation. Y prime could be y cosine theta minus x sine theta, and z prime would just be z. So this is a rotation in the xy plane. Now, when I say that all vectors transform in this way, if I was to look, for example, at the force, F might transform under the same rotation into F prime. And then let's imagine that F has got 3 components. So it's Fx prime, Fy prime, and Fz prime. What I mean when I say that all vectors transform in exactly the same way is that Fx prime would be equal to Fx cosine theta plus Fy sine theta. Fy prime would be equal to Fy cosine theta minus Fx sine theta, and Fz prime would be equal to Fz. Okay, so you can see that the force and the position have transformed in exactly the same way as vectors. Now, the reason why that is very useful is that it means that if we were to work out what is Newton's second law inside the new coordinate system, the one obtained by performing a rotation, we would find that F prime is equal to the mass times the second derivative of x prime with respect to t. So you can see that the equation looks exactly the same. And this is how we are able to write down equations which are facts about nature, and they become independent of the coordinate system that we use. Newton's second law looks exactly the same. It's exactly the same equation before and after the rotation. And this is why we use vectors. It enables us to capture something about nature and not something about our specific coordinate system. Newton's laws are the same in all coordinate systems, okay? And that's thanks to vectors. So that's why we use vectors. Now, let me mention something else. We might be interested in working out what is the position of our particle from the origin. So let me work out the position squared. So let me just clear a little bit of space here. I'll just erase that there. Good. So what is the position of the vector? It is given by, I'll just clean this, nearly done. There we are, we're done. So the distance squared from the origin, what is that given by? Well, the distance squared is equal to x dot x. This is just the dot product. You know what the dot product is. This would simply be x squared plus y squared plus z squared. Now, the distance squared from the origin is not changed by a rotation. And we can explicitly verify that. Let's take x prime dot x prime. So this would be x prime squared plus y prime squared plus z prime squared. Well, we've got x prime, y prime, and z prime above. So this will be x cosine theta plus y sine theta squared plus y cosine theta minus x sine theta squared plus z squared. So let's just expand this out. So you know how to multiply these brackets. We'll get x squared cos squared theta. The cross term is 2xy cos theta sine theta. And then we've got plus y squared sine squared theta. So that's from the first bracket squared. Plus, now let's look at the second one. Y squared cos squared theta minus 2xy cosine theta sine theta. And then plus x squared sine squared theta. And then we've got z squared. So now let's take a look. We can start to combine some of these terms. First of all, that cross term cancels against that cross term, no problem. Then we're going to combine this x squared with that x squared, and we're going to combine this y squared with that y squared. Okay, so first, the x squareds. X squared cos squared theta plus x squared sine squared theta. Well, cos squared plus sine squared is 1, so we just get x squared. Plus, now let's combine the y squareds. We've got y squared cos squared theta plus y squared sine squared theta. Again, cos squared plus sine squared is 1, so that's just y squared. And then we've got the z squared. So we see explicitly that x prime dot x prime is exactly the same as x dot x. And this is simply the statement that the distance squared is invariant under a rotation. Now, rotations are a symmetry of classical mechanics. So we can see that we've managed to make the symmetry manifest by writing our equations in terms of vectors. And we've seen that something like the dot product between two vectors is actually invariant under rotations. What we're going to try to do now is we're going to try to use Lorentz invariance, okay, to consider four vectors. And writing equations in terms of four vectors, we'll be able to write equations that don't depend on which Lorentz frame you're in. And we also want to write down things that will be invariant under Lorentz transformations. And that's the analog of this dot product. So that's what we're going to do next.